All right, we're going to pull back the curtain on one of the most fundamental, most important shapes in our entire universe. I mean, it powers our whole world, the screen you're looking at, the lights in your room, and yet it's totally invisible. So let's jump right in.
Seriously, have you ever stopped and thought about that? We plug stuff in every single day, but what is the actual shape of the energy that's buzzing around in those wires? Well, it turns out it's not just some random jumble of energy. No, it has a very, very precise and predictable form. The type of power we use in our homes is called alternating current, or AC for short. And that word, alternating, is the key to everything. It means the energy isn't just flowing in one constant direction. Instead, it rhythmically pulses back and forth. And that beautiful pulse creates a repeating, elegant pattern. And here it is. This gorgeous shape is called a sinusoidal wave, but everyone just calls it a sine wave. It's this perfect, smooth, repeating up and down curve. And look, this isn't just some abstract thing from a math textbook. This is the literal heartbeat of our electrical grid. Just look at it. It rises so smoothly up to a peak, then it curves back down through the middle, hits a low point, and comes right back to the start, all ready to do the whole thing over again. This graceful, continuous dance is exactly what's delivering power to your devices right this second. But to really get it, we need to learn how to talk about it.
So, to truly understand the sine wave, we got to learn its language. We need to know the specific properties that define its shape and its behavior. And what's so cool is, once you know these, you can describe pretty much any wave out there, whether it's electricity, sound, or even light.
Okay, first up, amplitude. The easiest way to think about this is just the wave's power, or its intensity. It's how high that peak gets from the center line. You know, a wave with a higher amplitude is like a bigger, more powerful ocean wave. It's just carrying more energy. For electricity, a higher amplitude simply means a higher voltage. Next, we've got frequency. This one is all about speed. It tells us how many of those full up and down cycles the wave can squeeze into one single second. Here in North America, our power grid operates at 60 hertz. That means the electricity in your walls is flipping back and forth 60 times every single second. That's just incredibly fast.
Now, right alongside frequency, you have what's called the period. They're a team. If frequency is asking how many times does it happen in a second, the period is asking, okay, but how long does just one of those cycles take? It's the duration of a single complete wave, say from the top of one peak to the very next one. And these two are basically locked together, right? They're two sides of the same coin with what we call an inverse relationship. It makes perfect sense when you think about it. If a wave has a really high frequency and it's wiggling up and down super fast, then the time for each little wiggle, its period, has to be incredibly short. And of course, the opposite is true too.
And finally, there's phase. This one's all about timing and relationships between different waves. Imagine two runners starting a race. If one of them gets a head start, even by a split second, they're out of phase. For waves, phase tells us exactly where in its cycle the wave begins at time zero. This becomes absolutely crucial when you're dealing with multiple waves at once, like in three-phase power systems.
So there you have it. That's our language. Amplitude tells us the wave's strength, frequency tells us its speed, and period tells us how long one cycle lasts. With just those three properties, you've got a complete blueprint for any sine wave. Okay, so we know what a sine wave is, but why? Why this shape? I mean, why isn't our power shaped like a square or a triangle? Well, it turns out this wasn't some random choice we made. The answer is actually really physical and honestly, kind of beautiful. Here's the secret. The sine wave is the direct physical result of how we generate electricity. Power plants use these massive generators, which are really just giant loops of wire that spin inside a magnetic field. As that loop goes around and around in a circle, the voltage it generates naturally rises and falls in, you guessed it, a perfect sine wave. That smooth circular motion translates directly into this smooth, wavy shape. So the real takeaway here is that the sine wave isn't just pretty, it's incredibly efficient. Because it's the natural output of a generator, it's the easiest to produce, it travels over hundreds of miles of power lines with very little distortion, and it's what makes motors run smoothly. In a way, nature kind of chose this shape for us. Now, here's where it gets really mind-bending. This pattern isn't just for our power grid, not even close. Once you learn to recognize the sine wave, you start seeing it absolutely everywhere. Think about it. That pure ringing tone of a tuning fork, that's a perfect sine wave traveling through the air. The colors you see are just sine waves of light with different frequencies. Radio signals, your Wi-Fi, even the gentle rocking of waves on the ocean. All of these things can be broken down and described using the same fundamental shape. It's a true building block of our physical world.
You know, this quote from our source material, Electrical for You, just hits the nail on the head. It says, "The sinusoidal wave is the most fundamental and basic form of any alternating signal. And it doesn't matter if that signal is something you can hear or see or use to power your house, its purest form is the sine wave." So we started with a simple question about a plug in your wall, and we ended up with a universal pattern that's woven into the very fabric of reality. It really makes you wonder, doesn't it? If a shape this simple and elegant is behind so much of our world, what other fundamental patterns are out there, hiding in plain sight, just waiting for us to notice them?